that was a lot of reactions. So you need to help yourself by taking some time to organize them some way. And everyone likes them a little differently. There's tables, charts, maps, all kinds of things. It's worth trying out all of them and see what kind of just really resonates with you. No pun intended. Okay, so let's try out a table. So some people are table people. So acid chloride, acid anhydride. So I like structures, so I am also going to draw them next to it. And carboxylic acid, but I like the word too because that helps me connect it in two different ways to what's going on. And the amide. Now notice that's also along the, I guess you can call it x-axis if you want, acid chloride, acid anhydride, carboxylic acid, ester, amide. Now let's go through this. What was nice about this table is that we've been spending all this time talking about what other things can do. We haven't really taken time to point out what they can't do and then put it all together. So start at the top. Acid chloride, what can they do? Well, they're not going to turn into themselves. So that's why there's X's all along this diagonal. But can acid chlorides become anhydrides? Actually, acid chlorides can become all of the things that we talked about. So that's an easy one. That's a yes all the way across. Acid anhydride. Here's where the reactivity difference comes in. They cannot become acid chlorides because they don't become something less stable or more reactive, but or at least not very easily, right? So there is the progression. Carboxylic acids are a little different because they have these workarounds with, like thionyl chloride. That helps a carboxylic acid turn into acid chloride, unexpected reaction. Now, normally carboxylic acids don't become anhydrides unless we have the diacid, right? Heat, usually. So it's a very specific scenario. Can carboxylic acids become esters? Yeah, that's Fischer esterification. And amide? Nope. At least not by any method we're going to be doing. It's not easy to do. Esters. Esters, can they become acid chloride? Esters are much more stable, and they're not like, they don't have that thionyl chloride option, so no. Esters will also not become acid anhydrides. Esters do get hydrolyzed to carboxylic acids, so we are going to switch to green for that. Can esters become amides? Well, yes. The only thing I'll put is a little mark here too for transesterification. I'll just abbreviate transester. There we go. So transesterification will be a way to convert an ester and ester, but it just has, usually the only reason you would do that is to switch out an R group. So as written, that's not going to happen, but or at least not worth mentioning. Amide, last one. Those are pretty unreactive. We are able to hydrolyze them. That's it. So that's useful to see kind of patterns of what things can do and what they can't do. Another way to look at it, other than the roadmap, which I still advise a roadmap, but this is basically a type of roadmap, I am going to call this roadmap the carboxylic acid reactivity ladder. So it's going to be a roadmap, but it's going to be structured to visually sort of represent the differences in reactivity. Okay, let's start filling in the rungs of the ladder. So carboxylic acid is like the godfather of this whole chapter. I am putting it on top. Really on the bottom. The foundation. So carboxylic acid, I'll abbreviate like that. Then, because it doesn't do very much, I'm going to have these kind of sorted by reactivity as they relate to the carboxylic acid. So amides are very unreactive and hard to convert. So it's going to have the next lowest rung. Here's my amide. Esters up next. Who's after ester? Who's more reactive? If we're going in increasing reactivity, it's anhydride. Finally, our most reactive of them all, the acid chloride. Now, we are going to fill in the reactions again, and this is where, before I do that, I'm going to kind of establish these levels that they're at. And they kind of correspond to relative energy levels too. So notice that the acid chloride is the highest energy of all the derivatives, so it's most reactive. And then by the time we get to the amide, it's lower energy, less reactive. Now they all can be hydrolyzed and turn into a carboxylic acid. So let's draw that arrow first, every single one of them. So it works in acidic conditions or basic. Anhydride as well. Basic's actually good enough. Don't need to activate that carbonyl, so you don't usually just see basic or just water and pyridine. So it could be pyridine instead. Acid chloride, water and pyridine as well. All right, so that's all amides could do. We're done with the amide section right here. That's all it could do is hydrolyze. Esters can become amides, yes. So we'll actually come down to this level. HNR, and just put excess in there. And that's all esters can do, because that's their relative reactivity. They don't become anhydrides. Now let's go to the next most reactive, anhydrides. They do more. They can become esters. You need some alcohol. They can become amides. You need some amine. Usually excess there too. And then acid chlorides, as we know, can do everything. So they can do the conversion to anhydride. What do they need? They need a carboxylic acid. ROCO2H is what I'm going to write to abbreviate that. And it helps to have a little pyridine to deprotonate it. Acid chlorides can also become esters and anhydrides. Oh, we just did anhydrides, excuse me. Esters are next. ROH and pyridine. Acid chlorides can also become amides. Where'd you go, amide? This level here. What do you need to be an amide? Excess amine. I'm going to turn it on its side to fit it in because I want to fit one more. H, N, R. It's H2 for that one. That amine has NH2. Excess. Actually, that particular one, the one I drew here, was NR2. So I take that back. I need NR2H. Now, those were all the arrows to what they can do, but then some important ones are that we can actually climb the ladder. So those are ones to really point out. I'm going to do this one in blue just so the color stands out a little more. So one of the big ones is that the carboxylic acid, when it can become an acid chloride, it's the gateway to all the others, right? So if you can let that, if you can get that transformation happen, then look, we can cascade back down to all of these. Any others that we can think about that go the other direction? So yeah, there's some that are worth mentioning. Carboxylic acids have some special cases, but they can become esters, right? So they're not going to they're not going to convert to an amide, but they can become esters, and they have special cases where they can become anhydrides. So I'm not going to include it here since it's a special case. But Fischer esterification. So ROH and H3H plus, usually concentrated. So that's the reactivity ladder. And what I like about it, it helps me kind of visualize to expect more arrows coming from the acid chloride, and the next most arrows coming from anhydride, and so on. So give that a try to see how that helps you keep these straight, because there's a lot of similar reactions. Mechanisms are simple, but the reactions are plentiful. So that's really the challenging part of this. So I'm going to keep this on its own short little lecture, and then I'm going to encourage you to keep this at your side as you do the homework. Signing out for now.